Okay.
Yeah.
Okay.
Can everybody see the slide fine?
Yeah, we can see the slides. Yeah.
All right. So today I'm going to talk about WESTPA, what it is, how to install it, and do a little demo. So WESTPA stands for Weighted Ensemble Simulation Toolkit of Parallelization and Analysis. And basically, it's the software implementation of the weighted ensemble method of Hoover and Kim. And a few weeks ago, Siddharth did a really good presentation on weighted ensemble for MD. So I'm not going to talk too much about it. I'll do like a brief summary since it's relevant for WESTPA. So if we have this sample conformational space, and we're interested in the rare event, the high energy region here. If we run just one system and advance it in time, it's going to spend a lot of time in this high probability area, not very much here. So it's an inefficient sampling of the regions that we're interested in. So the weighted ensemble method takes care of that by first splitting the space into bins and then forcing a target number of walkers, which just means simulations, or they're also called trajectories. It all means the same thing, I think. And so it forces a target number of walkers within each bin. And that way, we can more efficiently sample the regions of interest. And so this method is used for conformational changes in the structure of molecules from environmental changes, protein folding, binding of molecular systems. Okay, and so I want to talk about exactly how the target number of walkers is maintained, because that kind of plays into the splitting and merging algorithms of WESTPA. So there's two algorithms, like I said, splitting and merging. So if there's too many walkers in the bin, then some walkers get merged, and if there's not enough, then the walker will get split. And so in this diagram, the target number of walkers is 2. And so we start with one walker that has a statistical weight of 1. And the resampling process, that's what WESTPA does. It would split the walker into 2 walkers, and the weights get split as well. So then there's 2 walkers with equal weights. And then the actual MD dynamics part is run. And in this hypothetical example, one walker moves into the next bin. And so they both get split, and now we have quarter weights. And if in the next MD dynamic section, one walker moves back, then 2 of the lowest weight walkers, in this case, they're all the same weight, so it would be random. 2 of them would get selected, and one would be randomly deleted, and the other would receive some weight with 2 walkers. And it's based on their weights, which one gets selected. So this way, walkers get propagated through the conformational space, and we get to have equal computational time for all the regions of the conformational space.
I have one.
That's just the.
I have one question.
Yeah. Sure.
There is a possibility that a given energy band is non-contiguous in phase space. That means if you're on the top of your area, for example, that you cannot sample all that energy space without leaving and coming back. Is that being addressed?
Mm-hmm. Are you talking about like metastable states in between the initial and target states? Or?
They are all part of the energy. You're doing it in energy space, but that energy space might map to non-contiguous phase space.
Mm-hmm.
There might be, you might be on top of there, and there might be two different states on the top, which can only be reached by going through another energy region. How do you do that?
How do we what? Sorry, what was the last part?
I mean, wait, Well, I guess in the WE, like, the conformational space is divided according to the progress coordinates that we choose, which Dennis will probably talk about a bit later, but since we actually divide the conformational space up like according to the chosen progress coordinate, like there won't be any gaps. I mean, I don't know.
Why? Are you sure that there's only one path?
I mean, there could be multiple paths.
Yes, and
Yeah,
then
yeah.
you're lost. That's the problem. That's what I say. Then it doesn't work. And the question is, does it work? That is the code flexible enough to deal with paths which are non-continuous?
I think I'm not completely sure, but in one of the papers that I was reading, it said that the weighted ensemble method uses the initial free energy profile only as a reference, but it can generate new trajectories or newer or new configurations at the same as you said, like two existence of two different transition states or two different systems at the same energy.
Yeah, what I ask is kind of how do you make sure that the bins
Mhm.
are truly bins and they are not different. If you make your bins too narrow, for example,
Mhm.
then it is very likely
Mhm.
that you cannot sample everything in the bin without leaving the bin and entering again.
Mm. Wait, let me.
Okay, let's continue. But that's one thing you have to make sure, because first of all, how do you decide which space you're walking?
Yeah, that's always the hardest question. We need to choose the right progress coordinates, but I mean, I guess in practice, we go through like trial and error to see if this is gonna give us the pathway that we're interested in,
Okay,
you know? Yeah.
so technically, of course, you should. The problem is that technically you have to do it in phase space.
Mhm. Yeah.
And if we really do it in phase space, then we are safe. But of course, we don't know how the phase space looks like. That's what I'm saying.
Right.
So
I think there are two different interpretations of phase space, which the W takes into account. One is the equilibrium phase space, the equilibrium ensemble, and the second is the non-equilibrium ensemble.
phase space is outside of any ensemble.
So, I mean,
Phase space is always the states of any microstate. A phase space is not in an ensemble. A phase space volume is in an ensemble, but phase space itself is not.
Shouldn't it be the least action principle?
And no,
don't
you
that-
cannot assume that because you're not in equilibrium. That's the problem. Let's continue.
Yeah. Let's continue, Dennis. Yeah.
All right. So WESTPA itself, like I said, it's the implementation of this method.
Oh,
So it has,
Dennis, Sudisha asked the question, what is the
okay.
axis here? Like, yeah, free energy or potential energy, like in the previous slide? Yeah.
U of X. Probably, I mean, I'm not 100% sure. Isn't U potential usually?
Yeah, U usually denotes potential energy, but I mean, in this case, it's probably.
It has to be potential energy because you cannot measure the free energy of one state.
That's true, I guess.
So therefore it has to be a potential
yeah.
energy.
Yeah. Okay. Yeah.
Okay. Okay, so features of WESTPA. First, it's interoperable. It by default natively works with multiple MD engines. So Amber, GrowMatch, OpenMM, others. And even if it doesn't, it should be fairly simple to modify it to work with them. In that sense, it's very flexible. And I don't even think it has to be like an MD engine.
Is it a script or is it actually a code?
Sorry?
Oh, Roland's asking, is it a script or code?
Is WESTPA a script or code?
Yes.
It's code. It's coded in Python. It
So that's-
uses shell scripting to interact with the MD engine itself.
So Python is essentially a script. So code, I mean, it has to be, so does it have to be compiled or does it not have to be compiled?
Yeah, it doesn't have to be compiled.
Then it's a script.
Oh, well, actually, I guess you still have to install WESTPA using Conda, like Anaconda.
You need to create an environment.
Sorry?
You need to create
Create
a
it, yeah.
Conda environment.
Yeah.
Okay,
I actually installed it on HPC one
okay.
and mine, my workstation.
But essentially, it is not, it doesn't have to be, it uses libraries, but it doesn't have to be compiled itself.
Right,
We
yeah,
Okay.
yeah,
need
Yeah,
to
yeah.
have a compiler.
yeah.
Okay, okay.
It's portable, so it works on Unix-based operating systems, Mac and Linux. But this is a desktop computer I'm doing the presentation from, and I can get it to work, but you just need a Windows subsystem for Linux. WESTPA is scalable. That's where the name parallelization comes from. So in some of these simulations, depending on how many bins and walkers you have, you can get hundreds or even thousands of simulations per iteration. And so if these simulations are done on like large computing clusters or supercomputers, you can have like thousands of cores being used, with each core being responsible for one of the walkers. And it can be used on CPU cores, but it can also be used for with GPUs, depending on what kind of computing system it is. It's extensible, so there's a lot of plugins that have been developed for it. One of them is HAMSM, which when running a simulation, if you're not at steady state, it's not converged yet, you can use this plugin to estimate the steady state conditions and then restart the simulation from those estimates, which allows you to kind of reduce the time necessary to actually get to steady state. And WESTPA is also integrated with OpenEye Scientific's Orion Cloud Computing Platform, so you can use it with that, but it costs money. And most importantly, WESTPA is free and open source, so you have to pay money to use it, and you can actually look at the code, change it if you need for some specific purpose. And now I'm actually gonna talk about how to install WESTPA, what a simulation setup looks like, and a basic system that you could use as like a first look at WESTPA. So I'm in terminal now. And WESTPA 2.0 is very straightforward to install. You can just install it as a Conda environment. So you would first create the environment. It's Python 3.9. And I already have mine, so I won't run that. You activate the environment we're in now, and then you can just kind of install it. Yeah, so run that and you can get it. It's really simple. There's a way to just share the entire desktop screen, right? Because
I think you can, yeah, if you wanted to.
I don't have to like weird.
If you have more than one screen, you only can share one screen at a time.
Yeah,
You cannot share all your screens.
yeah.
Oh, that's okay. I'll just stick to terminal then. So
Yeah.
you can go to WESTPA GitHub and install like a sample system for testing. And in this case, we're going to do a NaCl system. So I'll just already have the thing set up, so I'll go there. Okay, so these are all the files that go into a WESTPA simulation. And I'll talk about exactly what each shell script does. So the first one is the environment shell script. And that one just sets the environment variables for the simulation. So the first one.
Oh, sorry, yeah.
Yeah.
Was it
Question.
Amber or Gromax? The tutorial.
This one is for Amber.
Okay.
I'm not sure if there's a GrowMatch one. I know there's an
Yeah.
open one as well, but yeah, this one's with Amber.
And
There-
the
there
dark
should be a
blue is
roadmap.
extremely
I
hard
know
to
it.
read.
Yeah. It is not
The dark, whatever is the dark blue font is almost impossible to read.
comments.
You can probably highlight it and then, yeah, you can highlight the text, I think. with
Oh,
your-
is it not visible?
Oh, yeah.
Oh, no, then it's yellow. Okay, never
The
mind.
yellow one is not.
Is that worse?
Yeah, it's just a fortunate choice of font, at least on this screen, so sorry.
Yeah.
Not your fault.
I'll share my file folder instead. I think it should be more
Okay.
visible from that.
Yeah.
Wait, you guys can't see the notepad.
No.
No, crap.
I can.
Yeah, no worries. Yeah.
Okay, so this is the environment shell script. It just sets up the environment variables. So Amber home, and you would have to actually denote that in terminal and set Amber home equal to wherever your Amber installation is, so WESTPA can use it. And then it sets up the WESTPA variables and the Amber tools that are necessary for the simulation. And then we got the next one up. Next script is initialize sh, which, as the name implies, initializes it. So it runs environment sh. It sets up the files for the simulation, the H5 file. And here it sets up whether it'll be an equilibrium or a steady state simulation. In this case, it's steady state because we're interested in the rate constant of the association of sodium and chloride. The next file is run sh. And this one, it runs a WESTPA file called w subscript run, and then it activates another shell script called run seg, which uses it sends and gets data from Amber for the progress coordinates of each iteration. And then the next file is west.cfg, the configuration file. This one's important because it's going to depending on what the simulation that you're running, you're going to have to change things in here. So for this particular system, NaCl, we have one progress coordinate, and it's just the distance between them. For other systems, you might have multiple progress coordinates in addition to just distance, depending on what you're looking at. You might have like bond angle or something like that. But for this, it's just distance. So that's our dimension of the progress coordinate is 1. And here you have the boundaries of the bins. So for this system, the initial state, I think, is around 10 angstroms. And if you can see here, the bin boundaries are not constant. So as we approach 2.6 angstrom, which is our target state, the bins become more fine. And that's because we're more interested in that region as the distance becomes shorter. And we want to have more definition there. And you set the number of iterations here, max total iterations. For this, it's set to 100. I think those are the important parts. And there's also information here for the analysis part, but I'll include some links at the end of these slides for all the important tutorial files and stuff, so you can look at it later if you're interested.
Mhm.
And also, I want to quickly mention the actual MD files that are particular to the simulation. So you have the Amber input file for NaCl, you have the PARM7 topology file, and then you also have the basis state as well. So those are all the important files for the simulation. So once you have those set up, running the simulation is very simple. Just share, go back to terminal.
Oh, actually, can you share the WESTPA scripts, like the scripts with the
Oh, yeah. That's a good idea. So these scripts are also important. Gen iState.shell, it generates the initial states of the system. And then get pcord script, it generates the progress coordinates for the initial state, and it's only used once for the initial state. And then for the rest of the simulation, it's going to be run segment script here that's used. And then post iteration script and tar segment script, that's used for data processing at the end of iterations, because when the simulation is running, there's a lot of files being created. And so these scripts, they kind of keep them organized into one file, the H5 file. Do you want me to actually open the scripts too, so you can look at them?
I think it's okay, yeah.
Okay. So then we go to terminal. We have all our files. So you run initialize.sh. I have an error.
Oh, I
Yeah,
think
well.
Amber is missing, but it's okay. I mean, you ran it before, so.
Oh, right. I forgot to set my Amber variable. I'll just do that real quick. Right. So it's important to set your MD environment variable, because otherwise it will not be able to find it. Okay.
I don't know.
Oh,
Control.
yeah, you're not supposed to have the $sign there.
Depends which shell you are in. Yeah, every shell is different there. Yeah.
Okay.
I know.
All right, there we go. So once you have the setup, you run that. You can just run sh, and you won't see anything happen. It'll just run in the background. But I have a completed simulation, so I'll just show the files for that. So as you're running the simulation, there's two files that are going to be updated, the WEST-H5 file and the WEST log file. And those are also going to be segment logs and trajectory logs. But if you look at the WEST log file, it'll just give you a summary of each iteration as it's completed. So you have the first iteration, the first bin is populated with 5 walkers, because that's our target number of walkers. And we can just see the information for each iteration. It tells you how many bins are populated. It tells you the sum of the weights, which you want always to be 1. Yeah, okay. So at this point, WESTPA has a lot of tools for analysis. So a basic one that you could do would be, in this case, we want flux data. So you could create a direct H5 file, and that's in the tutorial. But basically, I'll just show you what the graphs should look like. Talk about what they mean. This is the tutorial file, which again, I'll show at the end of the presentation. And so you can generate these kinds of graphs. This would be the probability evolution. And you can see as our initial state is somewhere around 10 angstroms, that's where the probability is centered. But as we go through iterations, it starts to spread and we get more information about the entire conformational space. And the flux data, which is relevant for this system, you can see it spikes and then it starts to converge, but 100 iterations, which is what was set for the simulation, is not enough to reach a steady state. So you would want to run it for longer. And then if you're calculating the actual rate constants for the system, you would not include these parts. You would only you would splice these out and use the parts where it's converged. Yeah. Professor Shirley, you want me to cover something else about the system? Or?
I mean, let's see, any questions so far? No. Well, maybe Dennis, you could just briefly talk about like what you're working on with the equal weight resampler.
Sure.
Yeah,
Yeah,
even though that's still ongoing.
I'll do that. Okay, so for the project that I'm currently working on, and this relates back to the splitting and merging algorithms. So if you look at the algorithms, you can probably tell that the weights are not going to be, they're going to change with time. When you're splitting walkers, the weights get split. When you're merging walkers, one walker will get total weight. And so the weights are sort of in the same range depending on the bin, but they're still going to be different, and you're going to have a certain variance associated with them. And so the purpose of my project is very simple. The error of the simulation depends in part on the variation of the walker weights, as you can see from this equation. So what I'm working on is a modified driver that replaces the splitting and merging algorithms with one algorithm that just works on a bin and balances walkers in such a way that you get target number walkers, and they each have the average weight of the bin. So the weights are evenly distributed among that bin. So the variance of the walker weights is 0, and that way the statistical error should be minimized. But it's still a work in progress as of now.
All right, yeah, well, let's thank Dennis for his presentation. Yeah. No, thank you. Yeah, I think, yeah, great job. Yeah, I think that was good. Oh, and yeah, summary.
Yeah, the link if someone wants to.
Okay.
Yeah.
So yeah, we'll post that on the website too, in case anyone is interested in using WESTPA. So yeah.
I have a question.
Oh, yeah.
It may not be for Dennis, it's like a question. So because you all are aware of WESTPA, so I'm like, just this question is like, for which scenario you feel like using this WESTPA enhanced stacking technique is important? Like for which scenario you're using this technique?
Mostly to calculate kinetic properties. I think it'll be useful.
But there are other sampling techniques too, right? So what is the like?
Not that many for rate constants, actually. Yeah, I mean, there's like milestoning and there's building Markov state models, but there aren't that many actually compared to thermodynamic methods. So yeah. Yeah, I guess what's nice about this method is that it doesn't add any statistical bias to the system. So which is nice. Yeah. But I mean, every method has pros and cons, so no
Yeah,
method is perfect. Yeah.
Yeah, that's why I want to know.
Yeah. Okay, well, yeah, thank you, Dennis. And I think next week we'll have Saucy, yeah, giving the practice QE again, yeah, before the final. Okay, yeah, then see you guys next week. Bye.